Hello everybody, welcome to another video of the regression analysis course. In this video, I'm going to talk about the similarities and the differences between the estimates obtained using OLS and MLE method of the parameters in a simple linear regression model. So let's start. We all now know what a simple linear model is when we have one independent variable and a dependent variable present in the model. It is y is equals to beta naught plus beta 1x plus epsilon. Here, y is the dependent variable, x is the independent variable, beta naught and beta 1 are the model parameters, and then we have an epsilon term, which is the error term, and it accounts for the uncertainty in the model. We have already seen a method called ordinary least square estimation method, in which we estimate the value of the parameters present in the model by minimizing the sum of squared error. And when we were using this method to estimate the value of parameters, we did not use any assumption we made on the error term. And when we minimize that sum of squared error, these are the estimates we got. Beta naught hat is equals to y bar minus beta 1 hat x bar. Beta 1 hat is equals to summation xi minus x bar times yi minus y bar divided by summation xi minus x bar whole square. And an estimate of sigma square is equals to SSE divided by n minus 2. And then we saw another method called maximum likelihood estimation method, in which we estimated the value of the parameters by maximizing the likelihood functions. But when we used this method, we actually used all the assumptions we made on the error term. And this is what we got as an estimate of the parameters. Beta naught tilde is equals to y bar minus beta 1 tilde x bar. Beta 1 tilde is equals to summation xi minus x bar times yi minus y bar divided by summation xi minus x bar whole square. And an estimate of sigma square using maximum likelihood estimation method is equals to SSE divided by n. Awesome. So we have estimates of the parameters using both the methods. And now let's compare the estimate of beta naught we have obtained using both OLS and MLE method. And it turns out that when we use OLS method, an estimate of beta naught denoted by beta naught hat is equals to y bar minus beta 1 hat x bar. And even using MLE method, we get the same estimate. So we have that an estimate of beta naught obtained using both OLS and MLE method are same. And since both the methods are same, we have already proved that beta naught hat is unbiased. And thus we have that an estimate of beta naught obtained using MLE method is also unbiased. Also, we found that the variance of an estimate of beta naught using OLS method is equals to sigma square times 1 divided by n plus x bar square divided by sxx. And therefore, variance of an estimate obtained using MLE method would also be the same. Perfect. And if we look at an estimate of beta 1, we have that an estimate of beta 1 obtained using ordinary least square estimation method is equals to summation xi minus x bar times yi minus y bar divided by summation xi minus x bar whole square. And it turns out that a maximum likelihood estimate of beta 1 for simple linear regression model is also the same. And therefore, since we have already proved that beta 1 hat is unbiased, beta 1 tilde would also be unbiased. And similarly, variance of beta 1 tilde would also be equals to variance of beta 1 hat, which is sigma square divided by sxx. Thus, we have that an estimate of beta naught and beta 1 using both the method are the same. And thus, the estimates obtained using both the method are unbiased, and we know the variance of those estimates as well. But what about an estimate of sigma square? An ordinary least square estimate of sigma square is equals to SSE divided by n minus 2. And a maximum likelihood estimate of sigma square is equals to SSE divided by n. Thus, we have that an ordinary least square estimate of sigma square is not the same as the maximum likelihood estimate of sigma square. And if they are not same, then what is the relationship between these estimates? We have that the maximum likelihood estimate of sigma square denoted by sigma square tilde is equals to SSE divided by n. On the right hand side, we multiply the numerator and the denominator by n minus 2. Once we have done that, we group n minus 2 divided by n together, and we group SSE divided by n minus 2 together. Once we have grouped these terms, we have sigma square tilde is equals to, we write n minus 2 divided by n as it is, and the second term SSE divided by n minus 2 is nothing but an estimate of sigma square obtained using ordinary least square estimation method, which we denote by sigma square hat. And we have the relationship between sigma square tilde and sigma square hat. That sigma square tilde is equals to n minus 2 divided by n times sigma square hat. Once we have the relationship, the next thing is we already know that an ordinary least square estimate of sigma square is unbiased. But what about an estimate obtained using maximum likelihood method? So let's check if the maximum likelihood estimate of sigma square is unbiased. To check that, we need to find out if expectation of sigma square tilde is equals to sigma square or not. If expectation of sigma square tilde is equals to sigma square, we would say that it is unbiased. But if it is not equals to sigma square, then we would say it is not unbiased. So let's check what is expectation of sigma square tilde. From the relationship between sigma square hat and sigma square tilde, we know that sigma square tilde is equals to n minus 2 divided by n times sigma square hat. Once we have that, we use the result that expectation is linear, and we can pull out n minus 2 divided by n from the expectation. And we have the second line, that is n minus 2 divided by n times expectation sigma square hat. In the next step, we use the fact that sigma square hat is unbiased. And since sigma square hat is unbiased, we have that expectation of sigma square hat is equals to sigma square. And we have expectation. And now if we look at this equation, we have that expectation of sigma square tilde is equals to n minus 2 divided by n times sigma square, which is not equals to sigma square. And thus we have that the maximum likelihood estimate of sigma square is not unbiased. Perfect. So if sigma square tilde is not unbiased, it means that this estimate of sigma square obtained using maximum likelihood method is biased. And if it is biased, then what is the bias value of this estimate? Let's look at the definition of how to find the bias value of an estimate. Let theta be a parameter and theta hat be an estimator of this parameter theta. The bias value of theta hat is equals to expectation of theta hat minus theta. So if we need to find out bias value of MLE estimate of sigma square, it would be equals to expectation of sigma square tilde minus sigma square. We have just found out that expectation sigma square tilde is equals to n minus 2 divided by n sigma square. And in the second line, we have sigma square in both the terms. So we can simply factor out sigma square. When we factor it out, we get n minus 2 divided by n from the first term, and the second term we get just 1. Simplifying this further, we get it equals to negative 2 divided by n times sigma square. And thus we have that the bias value of sigma square tilde is equals to negative 2 divided by n times sigma square. Awesome. So we have bias value of sigma square tilde. The next question is it asymptotically unbiased? So let's look at the definition of asymptotically unbiased first. Let theta be a parameter and theta hat be an estimator of theta. Then theta hat is asymptotically unbiased if limit n tends to infinity of expectation theta hat is equals to theta. It means that if we have a very large data set, that is the number of observation n is actually approaching towards infinity, then the estimate becomes unbiased. Let's try to find out if the MLE estimate of sigma square is asymptotically biased or not. So we need to check if limit n tends to infinity of expectation sigma square tilde is equals to sigma square or not. Let's consider limit n tends to infinity expectation sigma square tilde. We use the relationship between sigma square hat and sigma square tilde over here. And using this relationship, sigma square tilde can be written as n minus 2 divided by n times sigma square hat. Since expectation is linear, we can pull n minus 2 divided by n out of the expectation. And we have the second line, that is limit n tends to infinity n minus 2 divided by n times expectation sigma square hat. In the next line, we use the fact that sigma square hat, which is an ordinary least square estimate of sigma square, that is unbiased. And if it is unbiased, expectation of sigma square hat would be equals to sigma square. And now we need to take limit n tends to infinity of this term. So we would write the second term sigma square as it is, and the first term n minus 2 divided by n can be written as 1 minus 2 divided by n. And now if we take limit n goes to infinity over here, we have limit n tends to infinity 1 is equals to 1, and we have limit n tends to infinity 2 divided by n as 0, and therefore we have 1 times sigma square is equals to sigma square. And it follows that sigma square tilde is actually asymptotically unbiased. And we have the result that the maximum likelihood estimate is not unbiased, but it is asymptotically unbiased, which means that if we take n approaching to infinity, if we have extremely large data set, then the maximum likelihood estimate of sigma square also becomes unbiased. But what about the variance of these estimates? Is the variance of one estimate greater than the other, or is it the same? So let's find it out. We have already seen the relationship between these two estimates and have that the maximum likelihood estimate of sigma square, denoted by sigma square tilde, is equals to n minus 2 divided by n times an ordinary least square estimate of sigma square, that is denoted by sigma square hat, something we have already proved. So let's find out variance of sigma square tilde. Using the above relationship, sigma square tilde can be written as n minus 2 divided by n times sigma square hat. And if we look at the first term, n minus 2 divided by n, it is a constant. And using one of the properties of variance, that is that if we pull out a constant of variance, we get the square of that constant outside. We have n minus 2 divided by n whole square times variance sigma square tilde. In the next step, we use the fact that n minus 2 divided by n is actually less than 1. And therefore, the term we have over here, which is n minus 2 divided by n whole square, it is less than 1. And if this first term is less than 1, then we can write the second line as less than variance of sigma square hat. Thus, we have that the variance of the maximum likelihood estimate of sigma square is less than the variance of an ordinary least square estimate of sigma square. And these are some differences and the similarities between the estimates obtained using maximum likelihood estimation and ordinary least square estimation method for the simple linear regression model.